Okay. All right, so I'm just going to go over this, and I'll record it if you want to watch it later. So for Chapter 7, we're going to talk about linear regression. And so if you look at the scatter plot, it's talking about the total fat versus protein for 30 items on the Burger King menu. So they're just if something's on the menu, they figure out how much protein it has and how much fat it has. And this is the scatter plot of that. So the correlation in this example is 0.83. Using the value and the graph last chapter, we said there is a fairly strong linear positive association between the fat and the protein. In this chapter, we'll say more about the linear relationship between the two quantitative variables with a linear model. Okay, now whenever I say model, we're really saying equation. A model is an equation that we use to make predictions about behaviors between two variables. So the linear model is just an equation of a straight line that goes through the data. The points in the scatter plot don't all line up, but the straight line can summarize the general pattern with only a couple of parameters. It'll be a y equals mx plus b thing. The linear model can help us understand how the values are associated. The model won't be perfect regardless of the line we draw. As George Box says, all models are wrong, but some models are useful. Some points will be above the line and some will be below the line, and the estimate made with the model is predicted value denoted by y hat. So that little symbol there that goes above the y, we call that y hat. The difference between the observed value and its associated predicted value is called the residual. So to find the residuals, we always subtract the predicted value from the observed one. So you take a scatter plot, okay? And then you can create a model or equation. That equation will give you a predicted value. That's y hat. But then you actually observe it, right? So in other words, if I take, in this particular scenario, I have a new menu item, and I know what the protein will be, and I could use the mathematical model to figure out the fat content or vice versa. Well, let me go back to the graph so you can see it. So let's say I have a new menu item, and it has 40 grams of protein. Well, I can make that prediction that it'll probably have, 45 grams of fat, roughly. Now, I won't know for sure until I actually make the food, and then you have it tested. So whatever that value is, what I want to do, the residual is going to be the predicted value, y hat, this thing right here, and then the observed value, what it actually was when we did all the testing. So this right here, y hat, being on the line, and y, the residual, is a distance, okay? A negative residual means that the predicted value is too big, or it's an overestimate. A positive residual means that the value is too small, or an underestimate. In the figure, an estimated fat of the BK broiler chicken sandwich is 36 grams, while the true value of fat was 25 grams. So the residual value is negative 11 grams of fat, okay? Some residuals are positive, some are negative. On the average, they should cancel each other out. So we can assess how well the line fits by adding up all of the residuals. Similar to what we do with deviations, we square the residuals and add the squares. The smaller the sum, the better the fit. The line of best fit is the line in which the sum of the squared residuals is the smallest, the least squares line. So basically what we're about to do is we're going to go through and determine the line of best fit manually. This is something that we've been doing with the calculator or in Google Sheets, but this is the process that your calculator in Google Sheets does to determine the line of best fit. And basically there's a lot of math, but the math is basically going to find the distance from a line and try to minimize that distance from the line for each point in the data. So the figure shows a scatter plot of the z-scores of fat and protein. If a burger has average protein content, it should have average fat content too. Yeah. So moving one standard deviation away from the mean, and the x moves us our standard deviations away from the mean in y. Okay, so what they're saying is, if I move over here, then I probably should move over here. Generally, moving any number of standard deviations away from the mean in x moves us r times the number of standard deviations away from the mean in y. R cannot be bigger than 1 in absolute value, so each predicted y tends to be closer to its mean and standard deviation than its corresponding x was. This property of a linear model is called regression to the mean, and the line is called the regression line. Again, this is stuff that we've done on the calculator, but now we're going to learn how it's done by hand. So remember that a straight line is y equals mx plus b. However, in statistics, we write it a little different. We say y hat equals b naught plus b sub 1 times x. We write y hat to emphasize that the points that satisfy this equation are just our predicted values. It's not the actual data. So that's how we tell what is the real data, the observed data, and the predicted value for y. This model says our predictions from our model follow a straight line. If the model is a good one, the data values will scatter closely around it. Some will be a little above and some will be a little below. So then we write b1 and b naught for the slope and the intercept of the line. So b sub 1 is the slope, which tells us how rapidly y hat changes with respect to x. B sub 0 is the y-intercept. It tells us where the line crosses the y-axis. So that doesn't change much. Now, in our model, we have a slope b sub 1. So the slope is built from the correlation of the standard deviations. So b is equal to r times the standard deviation in y and over the standard deviation in x. So it's just like delta y over delta x. Our slope... I thought I turned my ringer off. Our slope is always in units of y per unit of x, okay? In our model, we also have to figure out the y-intercept, or b naught. The intercept is built from the means of the slope. So basically, we do the same thing that we normally would. Once you know an x and a y value, you can find b naught. Now, our intercept is always in units of y, okay? So it's just y bar minus b1 over x bar, or times x bar, sorry. So technology, we can do this on a calculator. I've shown you guys how to do that. I have a video. It's posted in Canvas, but we could do this a lot. We could use computer software. You could use Excel, but here at school we use Google, so Google Sheets has a program that you could use. It's built in. And then you can also use a table on the AP exam, but the any TI 8X, whether it's a 83, 84, 84 CE, and those are all approved by the College Board for AP exams. So if you learn how to do it on the calculator, you're good to go. So now let's look at computer regression. So R squared is a value that we consider. This is an actual, these are the calculations based on the scatter plot in this example. So over here we have the standard deviation of residuals. So that's a calculation that can be made. Our R squared value is 69%. Remember that R is the square root of that. So if you take the square root of 69, that's where they said, what did they say it was? 0.83, right? So 0.83. And then you have the independent predictor or variable. The protein is in the x-axis. The coefficient is 6.83. and that is the y-intercept. So this would be the y-intercept right here. The slope of the line would be 0.97. Okay. And then there's some data over here. We'll deal with this later on in the book when we talk about t-ratio, p-value. That's based on probabilities and the SE coefficient. Lastly, the dependent response is the y-value. Okay. So it's important to label that. In other words, we're saying the more protein something has, the more likely it'll have a certain ratio of fat. So the regression line for Burger King fits the data well, and this is the actual line. So this is what we call the line of best fit. Now the 6.8, that just means that's where it's going to cross the y-axis based on the data. So the data helps us figure out the line. The 6.8 is just going to cross the y-axis at 6.8. And then the slope, the general slope of the line in this particular case is 0.97. So the predicted value of the fat content in the BK broiler sandwich with 30 grams of protein is, you just plug 30 into the equation. So you would say 6.8 plus 0.97 times the protein value, which is 30 grams, and that gives a predicted value of 35.9. Okay. And then so the predicted value is the 35.9, and then we found out it was actually a little bit lower. So the regression line, since regression and correlation are closely related, we need to check the same conditions for regressions as we did with correlations. Make sure that your variables are quantitative. Make sure that it's straight enough, because you can run the math on just a cluster of data. So you want to graph the scatter plot and make sure it kind of looks like a line. And the outlier condition, you want to look for things that might be considered an outlier. So linear models assume that the relationship between the two variables is perfectly straight. The residuals are part of the data that hasn't been modeled. So the data is equal to the model plus the residual, or the residual is equal to the data minus the model. So in symbols, E, right, is equal to y minus y naught, okay? So residuals can help us whether the model makes sense, and help us to determine if the model makes sense. When the regression model is appropriate, nothing interesting should be left behind. After we fit the regression model, we usually plot the residuals in a hope of finding nothing. So now, if you look at this one, it says the residuals for the BK menu regression look appropriately boring. So then, I'm sorry, I kind of rushed through that. You could run the math on this one in the scatter plot. You know, the linear, this one doesn't look as linear. You can still run the math. So the standard deviation of the residuals, S sub E, measures how much the points spread around the regression line. Check to make sure the residual plot has about the same amount of scatter throughout. Check the equal variance assumption with does the plot thicken condition. We can interpret S sub E in the context of the data set. It is a typical error in the predictions made by the regression line. Oh. No, not this time. Okay, sorry. So then R squared is the variation accounted for. So the variation of the residuals is the key to assessing how well the model fits. In the BK menu items example, total fat has a standard deviation of 16.4 grams. The standard deviation of the residuals is 9.2 grams. So this is like a visual. I'll let you see. So if the correlation were 1 and the model predicted the fat values perfectly, the residuals would all be 0 and there'd be no variation. As it is, the correlation is 0.83. Well, that's not perfect. However, we did see the model's residuals had less variation than the total fat alone. We can determine how much of the variation is accounted for by the model and how much is left in the residuals. The squared correlation, R squared, gives a fraction of the data's variance accounted for by the model. 1 minus r squared is the fraction of the original variance left in the residuals. So for the BK model, r squared is equal to 0.83 squared, or 0.69. So the 31%, which is the complement of 69%, of the variability of the total fat has been left in the residuals. All regression analysis include this statistic, although by tradition it's written as r squared. And r squared of 0 means that none of the variance of the data is in the model. All of it is still in the residuals. So when interpreting the model, you need to tell what r squared is. In other words, we're looking to see what the variance is. And if you're at 0, the variance is just crazy, right? So there's this mix of I'm on the line or I'm not on the line. If I'm on the line, r squared will equal 1. That means that every data point is on the line. That's a perfect regression. However, the flip-flop of that is if r squared is 0, that means there isn't a single dot that's on the line or even close. So that's why we can determine things based on that r squared value, okay? So in the BK example, 69% of the variation in total fat is accounted for by the variation in the protein content. R squared is always between 0 and 100%, or 0 and 1. What makes a good R squared value depends on the kind of data you are analyzing and on what you want to do with it. The standard deviation of the residuals can give us more information about the usefulness of the regression by telling us how much scatter there is around the line. Okay. A common theme that you can do, sometimes, and this is why having a large data set is helpful, you might get sort of like an outlier, but you can filter out the noise by taking a lot of samples. And this really does have an impact on the r squared value. I could take 10 data points, or I could take 100 data points. The one with the 100 data points is far more revealing. But at the end of the day, we want an equation. If we have a good fit, we can use the equation to make predictions about something that we're doing, okay? Along with the slope and the intercept for the regression, you always report r squared so that the readers can judge for themselves how successful the regression of the fitting data is. So it's not enough, like let's say, to give you an example, let's say Burger King has a new marketing campaign where they're saying they have reduced fat, right? Come check out our low-fat menu. And they release this data, and they have some menu items that are far below the line of regression. But if the line of regression has an R value of 0.83, there's a little bit of variance there, so the predicted models and things like that just don't necessarily help. A better example would be like manufacturing. If I want to manufacture winter jackets in the winter, and I have a line that tells me exactly how many jackets I should manufacture each month, especially in the winter months, if I have a very strong correlation, in other words, if my model says I need to make 100 jackets, I'll probably sell 98, 95, you know. But if you have a weak correlation, I probably wouldn't make 100 jackets, even though that's the predicted value, because the correlation is weak. I might only make 80 and then play it by ear. So that R squared value is very helpful into determining if the predicted value, how reliable the predicted value is. Oh man, that's a lot of talking. So quantitative variables, the regression can only be done between two quantitative variables. You can't do this categorical. You need number values, okay? So make sure that you're always checking this condition. And it's got to be a straight enough condition. The linear model assumes that the relationship between the variables is linear. I like to use the example of my research at Notre Dame on thermal rectifiers. I was just collecting data like a crazy person, and I ran one linear regression, and mathematically I could do that. And I went to the principal investigator and I said, our R value and R squared is like bonkers. And he suggested that I needed to do a linear model for each phase of the carbon nanotubes that we were working on. So a scatter plot will let you check the assumption if it's reasonable. So when he told me that and I looked at the data, I noticed there were 2 clusters in the data, and that's where I was able, and the clusters changed at the melting point of the nanotube. So you got to look at the scatter plot basically, and that's helpful too. Okay, if the scatter plot is not straight enough, just stop. You can't use the linear model. Eventually, we'll learn how to do quadratic regressions and exponential regressions, but if it's not looking like a straight line, don't even do the math. They must have a linear association or a model won't mean a thing. So basically, when you look at the graph, if it doesn't look close to a straight line, you can crank through and do all the math and get an equation, but the R-square value would be so weird or low that the prediction is not predictable. It's not a reliable prediction. Some nonlinear relationships can be saved by re-expressing the data of the scatter plot to make it look more linear. So sometimes they'll take the data and run it through a log, and that can straighten the data out a little bit. Anyway, so it's a good idea to check linearity again after computing the regression when we examine the residuals. I like this term, does the plot thicken? So when you look at a residual plot for the standard deviation, the residuals, to summarize the scatter, when they say in other words, if you collect more data, does it look like the dots are still within the same range or the same distance from the linear model, the linear equation, the line, and they just kind of fill in the gaps a little bit better, or are they bonkers and far, far away? Outlier condition, watch for outliers. That really affects the math. Outliers can even change the slope of the line. So if you have some bizarre outlier that's way off the beaten path, you got to factor that in mathematically, and to get a line of best fit, you might have to change your slope. And because when it does that, what it wants to do is have that distance between the predicted value and the actual value be very minimal. And to do that across the average of all the points, you would be required to change the slope of the line, which impacts the intercept as well. So if the data seems to clump or cluster in a scatter plot, it could be a sign of trouble worth looking into further. Is it reasonable? Statistics don't come out of nowhere. They're based on data. So the results of the statistical analysis should reinforce your common sense. If the results are surprising, then you've learned something new about the world, or your analysis is wrong. Okay, in my physics class, we plotted some stuff, and it was a perfect correlation. I had an R-squared value of 1, but it's something that we did in class, and I was like, there's no way you have a perfect correlation. And I looked at it, and when I plotted the data, I plotted the same data. I think I did the time versus time, and that's why I had a perfect correlation. So you just got to look for those things. And then when you perform a regression, think about the coefficients and ask yourself if they make sense. There's some common sense stuff. You can even make a mistake in the math, right? So like if you have like an R-squared value of 1, and then you have like you're cranking through and you're trying to find the residuals, and those numbers don't seem to match up, you might have made a mistake somewhere. Here's where some mistakes will occur. The straight line to a nonlinear relationship. So you can run the math on something that might be quadratic. It's better to just run a quadratic regression or an exponential regression. Extraordinary points, whether it be y values or x values, if something seems to be extreme, kind of off the beaten path, don't extrapolate beyond the data. This is a common mistake. I can collect data for 100 years on the sales of jackets. I'll give you a perfect example. If I was a manufacturer of face masks, my model would not predict how many face masks needed to be produced in the years 2020 and 2021. Now, I'm sure there were a lot of businesses that made calculations and they manufactured And I think those numbers will go down as we come out of this pandemic. But that's why you can't extrapolate beyond the data. If you collected data until 2018, you can kind of make a prediction, but it's not the most reliable. Something can change. Okay. Don't infer that X causes Y because there is a good linear model for their relationship. Association is not causation. So even if you look at the explosion in mask production and sales, it doesn't mean it's related to the time of year or the time in human history. The causation is there's a global pandemic, so manufacturers had to make more masks. Okay? But you can look at the math and see that there is definitely an increase. How much of an increase? You can write an equation that shows you the increase, and there's definitely some sort of pattern of getting the mask out to all the people that they need to get out to. And you can do statistics on that. Don't choose the model based on R squared. Just because I've run into this too when I've done research. I've ran a linear model and had a fairly decent R squared value, and then I run a quadratic and have a better R squared value. So if the data looks like a straight line but it curves up a little bit, maybe you should try an exponential and see. Okay, so just because you say, oh, I got 0.85, or I got whatever the R squared value is, you go, oh, that's not bad. Sometimes if you try a different model, it's a better R squared value. When a linear relationship, when the relationship between the two quantitative variables is fairly straight, a linear model can help summarize the relationship. The regression line does not pass through all the points. It's the best compromise in a sense. It kind of fits through the middle of them. Okay, how do you find out where to put the line so it's in the middle of them? It's the smallest sum of the squared residuals. So when you do this on your calculator basically kind of makes up an equation and tries to see the distance for each point away from the line, and then it adjusts the equation, and the equation that you're left with has the smallest sum of the squared residuals. The correlation tells us several things about the regression. The slope of the line is based on the correlation adjusted in units of x and y. For each standard deviation in x, we are away from the x mean. We expect to be r times the standard deviations in y away from the y mean. Since r is always calculated between -1 and 1, each predicted y is fewer standard deviations away from its mean than the corresponding x. And r squared gives us the fraction of the response accounted for by the regression model. The residuals also reveal how well the model works. And remember, residuals is the distance the point is away from the line. If the plot of the residuals against the predicted value shows a pattern, we should re-examine the data and see why. The standard deviations of the residuals quantifies the amount of scatter around the line. So higher residuals, further away from the line. The linear model makes no sense unless the linear relationship is satisfied. Also, we need to check a straight enough condition and an outlier condition with the scatter plot. That affects the math. For standard deviation and the residuals, we must make an equal variance assumption. And we check it by looking at both the original scatter plot and the residual plot. Does the plot thicken? What's the condition? For your AP exam, make sure you can find all the values from the computer's regression output. The explanatory and response variables, those you got to label those. R squared and ignored R squared. You got to label the slope and y-intercept, and then you have to label S. Know how to interpret these values in the context of the problem. Make sure to include model words approximately, right? If you say, we're talking about observed and predicted values, when you use that terminology on the AP exam, it really solidifies your knowledge of that content. Without those words, you will not receive full credit. So you just write in the equation is not enough. You have to identify which one's the slope, which one's the y-intercept. Be able to take the square root of r to find the correlation coefficient r. And make sure you have the appropriate sign. Know that r is generally called the correlation coefficient on AP problems. So it's very highly likely that you'll get a problem where they'll give you the correlation coefficient, and then they may require you to know r squared. So you got to know that the correlation coefficient is r, and you take that number and you square it, and then you plug it in and finish the problem that way. So you really got to know this stuff. Know how to calculate the individual residual and interpret its value in context. Always write regression equations with the data, not x and y. You got to label y hat and the variable name. So if you just say y minus y hat, you're good. And that also helps you too, because I've seen students like get y and y hat mixed up and then they get the math wrong. But just by labeling y and y hat and saying that y hat is the predicted value and y is the observed value means that the kid was a little nervous and kind of got sidetracked. But that's it. Any questions? Man, that was a long video.